Okay, so let's start the final chapter of this short course. So in this chapter, I want to introduce the next generation of ALD, and then the ALD is now extending their lower to the like a patterning and an etching process using selective deposition and an atom layer etching process. So the conventional microfabrication is looks like we have substrate, deposits of film, PR pattern, and then etch out and remove the PR pattern. So this is the conventional microfabrication as I already explained in the previous chapter. So substrate again, PR pattern, etch out to make like a trench or hole system. So this is the like typical the process in our current microfabrication process. So if we want make some additional pattern inside this three-dimensional structure, how we can make that? So it is sounds like a really challenging because the etching process that is the very anisotropical because we use like a directional ion and then the radical to etch out. So we cannot make the additional pattern inside this three-dimensional structure. So how we can do that? So well, the concept is coming from the surface reactivity, the growth of the ALD. So this is some example. So if we have like a graphite substrate, this is a graphite substrate. Graphite substrate is very flat, and then some atomical stab edge. The flat area, like a terrace area, does not have like a high reactivity because the carbon bonding was very strong. But the stab edge area, has a lot of the dangling bond. So relatively is very high chemically reactive. So once we deposit some ALD material on this surface, so we can observe like a selective growth. So this is the platinum on the silicon oxide, very conform, very continuous and uniform, but on the graphite substrate, so some platinum nanowire is formed that is along to some specific line because they have like a dangling bond line. So this is the HOPG. This is the extreme case of the surface dependent growth of ALD. So this is the more extreme case. So the graphene, CVD synthesized graphene has the grain boundary, and then we deposit the platinum on that, and then we obtain the selective growth of the platinum. So this is the selective growth of the platinum along the grain boundary because the grain boundary is some kind of the defect, but there are some pristine side is very chemically stable. The platinum precursor cannot easily absorb on that, but easily absorb on the grain boundary area. We can see selective growth. So the results give a very good insight to us because if we control the surface property, so we can control the thick deposition of the ALD without anything. So surface property control can affect deposition of ALD. So this is the concept of ALD. So we have two different material, and if the one surface is blocked with other some the molecule, like for example, this surface property is changed by using other molecule, and then we just do the ALD, and the ALD nucleation is only taking place in this area, and then finally we can obtain the selective growth. So using this, we do not have any etching process. So the simplified, and then we can very easily obtain like a pattern without any like etching or powder lithography process. So how we can change the surface property? There are some two different methods: SAM, self-process monolayer, and a polymer. Self-process monolayer. So this is a self-process short like 3 nanometer monolayer. So if you have the silicon oxide surface, so this surface is changed to, well, once self-process monolayer is formed on this surface, the hydrophilic silicon oxide surface is changed to hydrophobic methyl andide surface because this SAM material is changed to the surface property by foam on self-assembly formation on that surface. So before SAM, the contact angle is very small, but after SAM, contact angle is very high because the chemical reactivity is changing. So the structure of SAM, head group, and an alkyl chain, and an end group. So head group is important, that is the chemistry on the specific surface. And alkyl chain, important, the molecular interaction and a packing density. So if you form like this, a lot of like a long SAM material, the interaction between this alkyl chain is pretty much important because this interaction can affect the blocking property. So the precursor cannot penetrate this inside this SAM coated area because this interaction is very strong. So end group, also important, determine the outer surface the property. So if you have like a silicon halide head group, like a silicon SiCl3 head group, strongly bonded silicon oxide, SH thiol, like strongly bonded the coinage metal, like a platinum, gold, silver, copper, and then phosphine acid head group, strongly bonded on the transition metal. So this is an example. So we have ODTS, SAM, silicon, substrate, pattern made by the typical phototherapy. After cobalt ALD for 1000, 2000 cycle, this is a AFM image. ODTS coated area, there is no cobalt, but only silicon area, there is cobalt because the contrast is oppositely changed. So that is the selective diffusion of the cobalt using the surface treatment. So polymer inhibitor. So polymer is pretty good. Well, the PL is also polymer. Polymer is a well-known material and a very cheap and easily controllable, and we can use a lot of things. So this is the example for the polymer inhibitor for the selective diffusion. We use the PMAMA. So after the PMAMA formation, so the platinum, ALD platinum was not formed on the PMAMA area. And then one good advantage of this polymer is water-soluble polymer. After the blocking and a selective process, the PMAM can be easily removable just by dipping in the water. So this is the with PMA, no platinum signal, and then without PMA, strong platinum signal. After removal process of the PMA in water, so we can deposit the platinum. Like surface is regenerated to silicon oxide again. So this is the the precursor inhibitor. So now in my group is now actively working on the precursor inhibitor system because the precursor has a lot of the big potential. So for example, precursor itself has a surface dependent growth. Like for example, ALD platinum growth is not very active on the silicon substrate, very non-uniform, non-continuous. But on the titanium oxide surface, very uniform, even in same deposition condition. That means platinum precursor easily absorb on the, like selectively absorb on the TiO2 surface only. And then counter reactant. So after the platinum precursor adsorption, we just put oxygen to deposit the platinum. Continuous platinum growth was obtained. But if you use the water counter reactant on that, so there is no growth. So using this concept, we use silicon precursor, which used for silicon PELD process. So that precursor selectively absorb on the silicon oxide surface and then reacts only with ozone and then oxygen plasma. So after so this is the contact angle of the silicon oxide. So very small contact angle, because that is surface, silicon oxide surface is hydrophilic. But after exposure of this DMA, DMS silicon precursor, the contact angle is abruptly increased, because once this precursor formed on the surface is changed to chemically inactive, like hydrophobic surface. So bare silicon oxide, many leucinium here, but DMA, DMS deactivated surface, no leucinium here. Well, can be easily like obtain the selective growth using the precursor inhibitor. So as I explained before, so one requirement for the ALD precursor is like there is no etching during the ALD reaction. So this is the some interesting report from the Professor Litala group in the Helsinki, and then they measure some increase of the mass during ALD process. But after some specific cycle, the mass is decreased. It looks like a real etching process, niobium oxide process. So the favorable reaction is the niobium chloride, and the niobium oxide is changed to niobium oxychloride. That is a gas phase. That is the flying away. This is the etching. So Professor Steve George and UC Boulder, the Colorado, and then they actively utilize this concept. They have aluminum oxide exposed to HF, and then aluminum oxide changed to aluminum fluoride, and they used to the tin agate, and then tin agate react with the aluminum fluoride, and then making some volatile byproduct, and then they remove this the surface. So the formation of the aluminum fluoride using HF is determined by the diffusion length of the HF. So that is a surface self-saturated reaction is also is taking place in the ALE process. Many reported ALD process. Aluminum oxide, cobalt, hafnium oxide, titanium oxide, zirconium oxide, and then silicon oxide and tungsten. But still, the many research group is working on that. So the concept of the atomic crafting, well, I really want to show the concept of atomic crafting. We have three-dimensional structure, selective growth, and then selective etching. Also, selective growth is material. Or we just deposit selectively here, only here, but not perfectly blocking of a selective growth material on non-growth area. We just etch out only here. So we can make the perfect selective growth using the atomic crafting. So probably the nano fabrication is composed of the deposition and the photolithography etching. This is the process, component. So, but I now believe ASD or atomic crafting process can be the sub process for the future nano fabrication. This can be used for like a toolbox. So this is the real example. So this is the copper interconnect and interlayer dielectric. But to make, well, this area is like 100 nanometer or like, for example, the 30 nanometer. So there are some error is taking place. The error is etch placement error. So if you have etch placement error, so this is close to the other line. There have the parasitic capacitance and then leakage. So to prevent that, so some researcher propose selective growth of the dielectric on dielectric. So if so this is the original dielectric. If it selectively grows on dielectric on this dielectric, so this distance could be increased. So we can prevent parasitic capacitance. So this is the real the application. If you use the error selective ALD, so we can make the selectively form this dielectric without any etching process. So can be used for that. But error selective ALD can be used for a lot of the application, because that could be used for like toolbox, and then like etching can be used for a lot of things in the current modern nanofabrication process. ASD will be used for that. Okay, so well, this is the contributor and then the reference.